definitely not.
Well, what's that divided by?
All right, so really important for me to show us how we've been going through this redox, acid-base chemistry, okay, combined, using volumetric titrations. Then we brought in the crystal field idea, crystal field splitting concept to talk about colors of transitional elements and how that opens the door for what? Color changes in volumetric titrations. But more importantly, it opens the door for using spectrophotometry, which I can use to measure how much color exists, which is tied to, because of Beer's law, all right, how much of the moles is dissolved. Like there's a tie-in that the more light being absorbed, well, the more chemicals in there, and that's how we use spectrophotometry. Measure the amount of absorbance, which is proportionate to the concentration. In that lab, we figured out how much concentration was in our solution that was dissolved by the brass. So how do I move on to gas laws? Because we've been hanging out with stoichiometry, mole ratios, and so I'm still on stoichiometry. And so before I do that, I want to make one more comment here and then show you how there's some serious connections in everything we've been doing. So there was an observation that I wanted to talk about. Now you can do your thing. So the observation I have is that when I gave you guys back your dissolved brass, and I just dissolved a shot right here, okay, there was a color to it. Now, some people noticed right away something that's pretty cool, and I think there's magic in chemistry. There's a lot of, obviously it's science and there's explanations, and sometimes our explanations we have to work on because we don't quite know everything. But there's certainly, to me, always a magic behind it. So here is, and boy, that's up close and personal, okay? But here is the evaporated dish that you guys obtained, and let me just get that. That's so up close and personal. And there's our evaporating dish, okay? And I'll kind of focus here, all right? And of course, everyone noticed that color right there, which is not really the color of the solution in water. And so I do want to explain, okay, what we have going on here, all right? And so the color here is that we had copper and we had nitric acid, okay? And so nitric acid, as we know, HNO3 is a strong acid. I would never write that this way, okay, in a net ion reaction. It becomes H plus and NO3 minus. Okay, now, the NO3 minus is what oxidized the copper. So we're going to have a lot of copper plus 2 in here. It's also going to oxidize the zinc, right? Because of the standard reduction potential tables, NO3 is such a strong oxidizing agent, it oxidizes both. So we have zinc plus 2. And because of understanding the fact that zinc plus 2 has a full amount of d orbitals, even though there might be some splitting, okay, due to the pulling in, there's no place for electrons to go, so there's no absorption of visible light, so this thing is clear. So the color that we use in spectrophotometry was due to what? It was due to the copper. But it's not that blue-green. This looks more what? And again, I'm not good in colors. Is it blue-green?
Yeah.
Is it the same color as it's dissolved in water? Okay, good. We'll go with that. Okay? So I'm just not color bright. I'm color, I guess, handicapped in a lot of ways. All right, so I have copper plus 2. Well, copper plus 2 is highly charged and small. Okay, so it's going to pull in. What do you think is the most prevalent ion in this solution? Okay, you can bet I added excess nitric acid. So what do you think is the most prevalent ion here? Besides H plus. If I added excess acid and this completely dissociates. Right, so NO3 minus. That's a ligand, it's not water. So the NO3 minus is going to get pulled in to the copper. So we've got this copper, okay? Now NO3 minus is bigger, all right? So it's probably going to be not as many, but the whole thing makes it complex. Still plus 2. Now, not plus 2, right? And so this is going to be what? Minus 2, right? Overall. This is plus 2. And this is another complex, okay? You say, well, why isn't there 6? Because there's 4, so this is making a complex. Now, this complex of NO3 minus pulls on electrons differently than the complex of water. Remember we had the water molecules getting pulled in? These are called ligands that are being pulled into the positive ion here. Well, when you change the ligand, this has a different ability to mess with the electrons in a different, what, orbitals than this. So now, what did you guys do? I said to dilute the solution, so I'm going to. And so what happens? So when I dilute the solution, as long as I don't miss. And so everyone didn't see that, did you?
I saw it.
Okay, all right, now, so what just happened there?
iPad, did you guys see it?
What just happened there?
It turned blue.
But it was blue-green and it went to blue. Are we good with the colors?
Yeah.
Uh-huh.
All right, so that's not blue-green. Now,
Red
we still have zinc +2. We still have copper +2. What just changed? I added a lot more what? Right, so this became copper H2O6 +2. They both still dissolve because they're both charged, so water can get around them. I just changed the what was being pulled in. So in crystal field splitting, the last little piece to this is based upon what is actually attaching to the copper will also change the what? The gaps. Okay, now think with me. This was a green, right? This was more of a what? Blue. Who is a higher energy light? Which photon of light has a greater amount of energy? Blue does. So blue has shorter wavelengths, green has longer. Okay, so blue has higher energy. So with blue, we're seeing blue because what part of the spectrum probably is being shown? If we see the blue, it's because it's absorbing the red or the yellow part, which is what? Longer wavelengths, and what kind of energy? Lower, which means the gap is high or small between the D's? Smaller. And a smaller gap results when I have water. Water doesn't split it as much as this one. The gap here is what? Bigger. And therefore, to go from here to here requires a larger energy of light. Okay, now green could mean that you're absorbing the what? Part of the red, but open the door for blue too. So changing the ligand changes the color because it changes how well it interacts with those as well. Another piece of that, okay? And that's just something that I think you should be aware of as you're going forward. Now, here's a different demonstration, okay? So I took copper chloride, okay? Now, copper chloride has this color. I added a little bit of water. It's this color because that's the ligand, chloride. As I add more water, water is more preferred, and it changes the color. So that's just something. But again, where is my connection to gases? All right, well, my connections is that, let me ask you a question, okay? Is there another way I could have figured out the percent by mass of copper? Is there another way I could have figured out the percent by mass of copper? Think with me for a second.
Wait.
Here was the chemical reaction. Copper being oxidized, and zinc, okay? But here, this was happening, okay? So here's a reaction of your what? Of your brass shot. Here's me pouring really quickly, okay? What am I producing? You see fizzing. I'm producing NO2 gas. We have balanced this reaction. Could I have collected possibly a way to collect possibly this brown gas and measure how much volume? And don't we know that volume can be related to how many moles of a gas? Couldn't I have used the moles of the gas released and find out what? Find out the amount of what? Moles of copper reacted by the balanced chemical reaction. So the party people, yes. I just conveniently skipped that. What other reactions have we worked with? Did we drop acid onto sodium bicarbonate and sodium carbonate, baking soda and washing soda, and it fizzed? We let the carbon dioxide fizz, but then we took the solution, which was water and salt. We boiled off the water. We measured the salt to do stoichiometry. Couldn't I have measured the CO2 and gone backwards? Absolutely. Think of this even further. September. Didn't we do electrolysis? And didn't we collect a gas at the anode? Okay? Didn't we do a copper chloride solution? Anyone been smelling chlorine gas in here a little bit? because I made it in the underwater fireworks. But didn't we have that same smell when I took the copper chloride solution and you took the 2 graphite electrodes and you collected the copper? There was a little bit of bubbling on the other, and we made chlorine gas, Cl negative, being oxidized, anode. We've been having this all over the place, okay? We just have been not considering the gas till now. So my connection to you is we could have done this lab by measuring the gas emitted, okay, and circumvented the entire spectrophotometry. But not always easy to work with gases. You have to collect all the gas. You have to have a certain set of conditions. And gases have their own set of laws that they behave differently, because gases fly around the room hundreds of miles an hour, okay, whereas liquids will stay in the container, okay? So there's extra precautions, extra types of things. So that's why I'm waiting till now to talk about the stoichiometry of measuring this. But think about its implications. Remember, I did this demonstration where we split water into the 2 gases. And at the oxidation at the anode, we produced oxygen. And at the cathode reduction, where we reduced water, we produced what? Hydrogen. And if you remember, I told you, why was there twice as much hydrogen gas produced as oxygen gas? Based on our mole and particle theory, there's twice the amount of what? Hydrogen in a molecule of water. Double the volume, you double the amount of particles. This was known for a long period of time. This is like a phenomenon. Take water, add electricity, and you get this. John Dalton didn't consider this to be in his chemical equation. Remember, he thought water was a HO, H-O, okay? But there was definite telling you that there's 2-to-1 ratio. So there's implications everywhere. So many different reactions. When I made zinc, when I made the balloons that exploded, I could figure out how much zinc I needed to produce how much volume of what? Of a balloon I wanted. So there's a whole set of conditions. So gas laws, of course, been around. And now we're going to dive into them, all right? And we're going to see how we can continue on our understanding. I hope that's a good enough transition, because I really believe it's another way for you to think about these types of stoichiometry problems. So, what can we do with gas-generating reactions? We can determine the limiting reagent. We can determine the amount of reagents, like we've been doing. We can do a percent by mass. We can determine empirical formula, the molecular formula, determine the amperage that it takes to make this electrolytic cell. So we can basically do what we've been doing before, but now we're going to deal with the phase of gases. All right, so any case, before I can get into the gas laws, I need to tell the story of someone called Torricelli. It's where it all began. He was the first person to do any kind of quantitative analysis of what pressure does, and he did so, and this is why I love it, based on an important application. No one just sat and think, well, what's pressure? He was out to solve a problem, and in that problem, he built something called the first manometer, okay, or called manometer, and I'll explain that in a second. So let me just take you to that. Let's get this solution out of here. As we now talk about, okay, Evangelista Torricelli, okay? So in any case, let's go to slide, what did I say here? 27. Am I being salty by saying? Probably am. Okay, so Evangelista Torricelli. So look at the years here. Way before the idea, way before the possibility that you think there may be atoms. Remember, the one person to bring back the atom concept, if you remember the time period, was a little bit after this, was someone named Boyle, Robert Boyle. In fact, he was so scared to talk about particles of matter, he wrote a play where his actors or whatever, his characters discussed chemistry. He didn't do it, the characters. It was art, okay? I feel like if I mess this video up, it's just gonna be art, right? It's a great thing. If it's dots on a page, whoa, it's art, okay. So any case, so let's talk about Evangelista Torricelli, okay? And again, time period is, he was about the end point, if I'm not mistaken, around Newton and a couple of other important people of the day. So any case, he was after to solve a problem, okay? And to solve the problem, he needed to understand, how can I measure what's causing the problem, which wound up being pressure. Okay, just stay with me, all right? Again, I feel like someone drew the mustache on it like that, but hey, who knows? All right, so here is the pump, and this was called a Leonardo da Vinci pump. This is what the designed by Leonardo da Vinci. Okay, now I'm going to try to draw it to make some sense of this. Okay, so there was a pump outside the city walls of Tuscany, and as you can understand, cities were still cities. Some cities in Italy were, or I think this was Italy. Any case, were city-states. Even though they might have been part of a bigger province, they still had to protect themselves. So there was definitely still city walls here, all right? And so there was a pump that pumped the water, okay? Now, I don't know if it's one pump or a bunch of pumps, but they gathered their water outside the city gates. And so how the pump worked is, of course, you have the land here, okay? And you have the pump that sits up above it, and it's got an encasement that's open. It's got a tube, okay? Now that tube goes into the ground until you get to the water table, okay? And this might be the water table. I'm sorry if the water's purple, just the way it goes. All right, so there's the water table, okay? So that's where the water has hit an aquifer. All right, now how does the pump work? Okay, well, the pump is like a piston, probably not bent like that. And so the pump has some kind of, see, now they didn't use plastics, but it could have been some kind of, I wouldn't say rubber, but probably some kind of circle that had either leather on it or some kind of lubricant that would act as a seal. You had to make some kind of seal, okay? And that part I'm not really sure what they used, all right? Of course, there was a spout to get the water, and of course, there's a mechanical device to pull this piston up. All right? And it's sealed a little bit, and then we're attached to a handle. And of course, the handle had a little pulley device that you could pull it down in, okay? So again, the idea here is that you could pull it up and pull it down, and I guess we want to pull it up. Okay. So how the pump works is pulling the handle up, and the handle goes up this way. You with me? Now, if the handle goes up, where's the plunger going to go?
You're gonna have to squeeze it.
Okay, so I guess we want to squeeze it. My bad. The way that I put it here. So if I squeeze it, okay, it's going to go up. My bad. Okay, thank you. So when I squeeze it, the pump is going to go up. Now, you look what we have here is that water gets pulled up into this reservoir here. Now, there's a reason for that. When I pull the handle down and make the space bigger, right? Because this is going, I guess I should have drawn it like this. For those that are questioning my design here. Okay, so you got to start that way. My bad. All right. So when I push it down, okay, when I push it this way, the handle. I don't know if it's a fancier handle, okay or not. Okay. All right. I'll make you focus on that. All right. Now, as you push it this way, clearly the plunger is going to come up. Now, here's what happens. We have gases, particles here. We didn't know that then. He didn't know that then. He didn't know how this worked, actually. But we know now that the gas is above the liquid. Now, you can think of it this way. There's gas above this liquid. We can start with the liquid right here. Okay? And so what we have, clearly, is we have air, molecules of air, which we know is nitrogen and oxygen, all filling this space above the liquid. You with me? Now, as we push in and make the plunger go up, okay, what we're going to do is we're going to create what? More space for the same gas particles. Okay, that's terrible. So let's pretend it goes up this far. Okay? And so what happens is there's more space for the same gas particles. And if you do that, think about it. You guys are bumping around in a room, and if I keep everything else constant and give you more space to fly in, will you collide with the container walls more or less?
Less.
Less. Pressure drops. Pressure is due to collisions of molecules, gas molecules, with their container walls. If you make the space bigger, keep everything else constant, the pressure drops. So, by pushing this in and making the space bigger, the gas molecules have a greater space to travel in. And so what we've created is a low pressure area in there. We've created a partial vacuum. Now, in the aquifer, okay, you have water, but you also have what? Air. And the air bounces around too in all directions. It bounces to the top of whatever that vessel might be. It also pushes down. So there's a pressure that's pushing down on the water. So when you lower the pressure by putting the plunger here, okay, the higher pressure that's maintained inside the aquifer actually pushes the water up. Okay, that's how the pumps work. Now, they didn't know how the pumps work. I'm explaining that first. So, they had this pump, it was outside the city gates, and it was working fine. Okay, Leonardo da Vinci created it. Now, the idea was that supposedly that we want to protect this pump, and we don't want to be able to go outside the city gates and possibly get attacked. We want to bring it within the walls of the city. Now, the city-state of Tuscany is elevated. So, it's elevated for a reason, because it's better protection in an elevated spot. So when you move this pump to an elevated region, the problem was, okay, that they had to build it deeper to get the water. Who cares? Same pump, but they had it a little deeper. And so they would, all their might, push down and not get the water. And the pump did not work inside the city gates. And they didn't know, and they asked their most important, or at least they thought was the person who could solve the problem, what's his name? Torricelli, let me get it. I can do this. Evangelistic, whatever. Who's of Italian descent? Evangelista Torricelli. Good enough. All right. So he was thinking about this, and he said, there's something about the fluid of water. We're trying to move fluid of water a long way. Now, he knew that this depth was a certain value, okay? And that value, I don't think they were using feet or meters then, so I don't know what kind of unit of length they were using. But he knew that it was deeper, okay? And that depth, we have 2, right?
Yes.
I'm going to keep going, okay? If you need to leave for water or something. Any case, that depth, okay, was greater than this. And he said, wait a minute, to pump the water, water has to travel and be pushed up a longer distance. And he knew, and he thought about this, water in a tube is going to have incredible amounts of weight. The forces acting on this, okay, the forces acting on the water, whatever that force might be, can't move that much water. So he wanted to build what most scientists build. He built a model. But he couldn't build a model with a tube of, again, this is about 30 or 40 feet of water. He couldn't build that. So he said, how can I make this manageable? How can I make this manageable? He said, well, how can I build a model to test my theory that it's about the weight, some force acting on the weight of a tube of water? Okay? And so what he said was, I'm going to use a liquid that is 13.5 times more dense than water, and see what happens. And that, of course, was mercury. And I used to be able to do this demonstration live. And I would take a tube, which is called a Untitled tube, and I used to fill a vat with mercury. I would pour the mercury into my tube, okay, and I would invert it. Now I can do it with water, okay, and I'm gonna try. Okay, it's not as crazy as mercury. So this is exactly what he was trying to do. He wanted to see if any force in nature can support columns of liquid. And of course, I'm using what? A 1.5 foot column? The column he wants to test is probably over 30 feet. So if you take this, invert it, put it underwater,
It doesn't do.
okay, yeah, you can see that the water didn't fall out. Now he said there's some force in nature that's supporting that column. What's that force in nature? Well, we now know it's due to the molecules slamming against the liquid downward and forcing the water what? Up that column. Okay? And he says, wow, water's pretty light. Now to test his theory, he had to build a column over 30 feet, somehow cap it, invert it into a column. Totally impossible for him to do that. So he said, well, he was smart. What if I do this a different way? Okay? So he said, what if I use a liquid that's 13.5 times more dense? And that was mercury. He thought about this. And so he filled the same container. Now, the tube would be about a meter long. In fact, I'll show you the tube. It's called the Untitled tube. And I guess I should have done that. By the way, that's water with food coloring, because so you can see it. Water is not really blue. Okay? All right? So, so here's the Untitled tube. Yeah. Well, I don't care. We're using this. So he filled this, and again, I can fill this also with water. Okay? And this is a 50 milliliter, so I should have enough. And it doesn't matter the size of the tube, as you're going to figure out that pressure is force over an area. So if I have a bigger tube, okay, I need more force to support it, but it's over the same area. So pressure is a force over an area. So I do the same thing. I'll knock that one over. And you can see that the force due to nature is still hitting this liquid and supporting this column. Now, he did the same thing with mercury. And he said, well, I can't build a tube, 13.5 times higher, but I can use what? A liquid that's 13.5 more dense. And I'll explain the difference there. He did the same demo with mercury. You started with a vat of mercury, filled it up, and when he did it, the mercury dropped. This column, which was about a meter or so, you couldn't support that much mercury. Mercury is what? Heavier. So guess what? He measured this height that mercury can be supported. Remember, gases are hitting this. And he measured that height. We now know it to be 760 millimeters of mercury that can be supported up a column. What did he get from that? Now we know he didn't have millimeters then, but he measured that height. What did he get from that? Wait a minute. If a certain distance of mercury can be supported only by the force of nature, probably due to air pressure, multiply that by 13.5, and that's the limit of how much water can be supported. That makes sense?
Yep.
So if I pick a tube and drop it out the window, maybe I'll do this tomorrow, fill the tube up and invert it down below, it should, I think we're over 30 feet. It's gonna drop. We can't support almost 30 feet of water. So there's a limit to how much water can be supported in a tube. What's that limit? Air pressure. So what was their problem? I'm gonna take this is gonna fall and break, and these tubes are really expensive. So there's a limit to how much liquid. Not in what? The limit wasn't reached here, but the limit was here. And what's the limit? The limit was, when you create this pump, and you create a low pressure area, what's really moving? What's really moving? Yeah, the air pressure is moving. And air pressure, the force due to air molecules hitting a liquid, can only support, as we're going to find out through your homework tonight, only about 30 feet of water. That's when you dive 30 feet, you feel a second atmospheric pressure. 30 feet of water, okay, the weight of 30 feet of water is approximately one equivalent of natural gas pressure that we're normally under, called an atmosphere. Okay? So he was the first to do what? To discover a barometer. And again, here was his vat of mercury. He took a tube, he filled it with mercury, inverted it, and he can only measure, it can only support this distance. Whatever this distance was, he times it by 13.5, and that's the limit due to water. Because water is 13.5 less dense, it can be supported 13.5 times higher, as Connor said. All right, and he found a limit to what can be supported. So this doesn't work. This system will never work, because trying to exceed the limit is what they were doing in the city-state. By having the elevated position, they were trying to push water using atmospheric pressure, okay, greater than it could. Atmospheric pressure is only a certain value, and it just wasn't high enough to push it that far. So he built another pump, and he changed this, okay? And what he did was, and I'll have to change a little bit, was he made a little hole here, okay? And he had an air valve, okay? And so what you did was, when you pushed it down all the way, and this came up past the hole, air did what?
Went out.
No, well,
Oh,
went in because it was low pressure. And then when he pushed it back the other way, okay, he pushed this downward. And what was he doing with the air that he added? He was compressing it. He was putting more gas in a smaller area, okay? And what he did was he pushed and bubbled extra what? Gas or air in this area. And by adding more what? Adding more gas molecules to this area made this pressure do what? Go up. And therefore, once he pushed the air down, okay, then it would spill out. So he made a pressure valve, okay? And that's how your what? Tire pump works. Same thing. You go up past the air, then you catch it and you push that in a smaller space. And so he built a new pump and solved the problem, okay? So again, that's what he did, and that's the story, okay? Now, there were people that tried to test his hypothesis, and they were successful many years later, okay, by seeing how much water could be supported. And these are some pictures I found. I guess these are drawings, obviously, all right? So he used a force pump. The force pump was how it works, and it's the same pump that we use to pump our tires. So why was it so important, his work? Because he built something called the first manometer. Now, if you're a sexist, manometer, hey, all right? And what's a manometer? A manometer is a device, or a manometer, that doesn't measure the manhood. It measures, of course, it measures pressure against a known value. Oh my gosh, it sounds like a titration. So what's a manometer? Well, this was the first one. They later called it barometer, but it's really a manometer. Why? Because using what? The atmospheric pressure, and assuming that there's no what? Competing pressure in here. If you start with pure mercury and it drops, this is going to be a vacuum. Now what's a vacuum?
Sucks it up.
Right, 2 U's, right? I feel that's wrong, but anyways, a vacuum. So there's nothing competing, there's no gas particles here. So what's supporting this column? And I can measure the pressure. So he started measuring pressure with millimeters of mercury. Why not water? If I wanted a barometer of water, I have to walk around with a barometer that's 30 feet tall, instead of working around something that was what? 760 millimeters, 0.7 meters. We later found out that height is 0.760 meters. So he was the first to discover something called manometers. Okay? Now, what's a manometer? Well, let's go to our worksheet. Okay, the first one that I did not give you yet. Christmas in July, people left. All right? And so here's the manometers. And this is, anytime, and we're going to see manometers appear all over the place. Oh, great, you're the best in your area. In her area too, I guess. So manometers.
Thanks.
Oh, man. You bet. Everyone got one? Got one? Okay. So let's go to the manometer. Worksheet. Now, I'm going to give you an example of a manometer. Now, barometer is an example because we're going to use atmosphere. We can actually measure atmospheric pressure by using the height of a column of fluid being what? Supported. And that's important, party people. The height of a fluid in a column was the first place we measured something called pressure. And here is an example of a manometer. And there's many examples, okay? So here is my example, all right? So now I don't have mercury, I've got water, but we can pretend it's mercury, okay? All right? Am I getting that on there or no?
No.
So everything I just did here I didn't get. Awesome sauce. Okay. Yeah, whatever. Okay, so can you see this now?
Nope.
All right.
Do you want me to just stand there and hold it?
No, definitely not. Because I'll never go back. So let's do this. I should have moved that over. Could have been the perfect video, but it wasn't.
Yeah, but next
All
time
right.
you don't get-
Can you like edit it?
I could. This is more work though, right? My team of audiovisual and lab agents. Sometimes you have to realize it's just me, little old me doing this. How we good?
No.
I'm not in there?
No.
It's gotta be higher?
Yeah, why don't you move the table over and then put the block on top
Christmas
of
in
it?
July. Okay.
There's so much stuff right there.
I like my stuff. I like my stuff. Maybe. All right, I'll go with that. This thing has been there for like months.
We
All
just
right.
got 6.02 times 10 to
Oh, I love you.
the 23.
I'm gonna knock this over at some point. That's gonna be a good time. All right, so let's talk about a manometer. At some point, you'll be able to see it, and I guess I have to edit this part. All right.
Maybe they do certain things before.
I like when it ghosts and you move over. He's magical. No, he's tall. Okay. All right. I don't know what's gonna fall apart here. Oh, Christmas. Yeah. See, that's the problem with me. Yeah, good. We're gonna move over. Yep, I'm doing the best in my area. Okay, yep, I need all of this, right? Okay, so
It's on.
what we have is our manometer.
Grodsky, watch out. Your left side is on top of something. Left side.
You might want to put the block on top of the table.
Is that covered?
What block?
Still can't see
That
it.
block.
The 6
You
foot
can,
you
like,
can
you
10
can't
to
see
the
the bottom
23.
of it.
Christmas, really?
Really mess us up, Brian.
All right.
Oh my God,
Thank you, though.
it's here.
All right, so at some point, we'll get this set.
Oh my God.
You know I'm breaking something. All right.
Stall
There you
everything.
go. You're
All right.
It's a little high.
All right, so. Yeah, now it's too high. All right, so. I'm going to take this syringe off, and if you look carefully, you see that these levels are equal. Now, there's a reasoning. This is a closed tube that's connected to it's really an open air tube. This is a aquarium tubing. It's open and it hits this side. So the air going into this tube, its force per area slamming against the top of this liquid is the same as the what? Open air. So therefore, we have the same pressure. And therefore, when I look at the difference of the pressure above this liquid and this liquid, hey, these levels, of course, are equal. There's no difference in the pressure on one side or the other. Remember, this could be mercury. Let's pretend it is. It's not. Okay, now, I'm going to put a syringe. Now, a syringe is the same kind of plunger that was being used in the Tuscany. The syringe, okay? All right, now, I'm going to basically tie this in at some point. I'm going to push this in first, okay? And we're going to do what the first, okay, type of pump that Evangelista Torricelli used. Okay, so he's going to pull up and create a what? Bigger space. Remember, now this is now sealed. So by giving the gas that's in here more space to fly in, isn't it going to hit the top of this liquid less?
Yes.
But I'm doing nothing to the gas hitting on top. So what's going to move this?
The right side. It's gonna go right.
All right, well, yeah, it's definitely. So if I pull back, I'm creating a difference in what? Fluid being upheld. Why? I just made the space bigger, so the pressure dropped. Who really pushed this forward?
The pressure.
The pressure in the air is greater than the pressure here. How can I figure out exactly what that pressure is? I can actually measure the height of the differences in the column. So if this was mercury, I could measure, and let's pretend that's at a 2, and that's at 16. I'm just making those things up. So a 2 to a 16 is a what? If I'm at a 2 here, that's where this level starts, I'm supporting this up to, let's say, 16. I'm supporting 14 millimeter, in this case, centimeters. And a centimeter times it by 10, I'm supporting 140 millimeters, let's pretend it's mercury, up. So who's winning? The gas here or the gas in my syringe? The gas in the atmosphere. How much higher is the gas in the atmosphere? 140 millimeters of mercury. Let's say I know the atmospheric pressure is 800 torr, which is millimeters of mercury. What? Okay. What's the pressure in here? 800 minus 140. It's 140 less. I'm using the known pressure here and the quantitative value of how much what? This is winning. Think about it. The gas in this area here is not only pushing and supporting 140 milliliters of mercury, isn't it also pushing away the air on the other side? So it's winning by 140. This gas here is what? Greater than the gas in this area here by 140. And I can do the opposite. It's a manometer. Why is it a manometer? I'm basically using some kind of comparative analysis, in this case, fluid in a column to measure pressure. Okay, so I relieve the pressure. It goes equal again. Okay, now we'll start. This is going to be the force pump.
No.
Okay,
You're gonna put more in.
and now I'm going to take the space. The air in here has the same pressure on this liquid as here. Now by making the space smaller, I'm increasing the pressure. Let's pretend the same thing happened. I'm at 2. The levels at here are 2. And this is 16. Those are centimeters of mercury. We'll pretend it's mercury. Who's winning? The pressure in this container is 140 millimeters of mercury higher than the pressure outside. The pressure outside is known to be 800. What's the pressure outside? 800 plus 140, 940. So manometers use a known value of pressure and the support of how much liquid. Think about it. It's not only pushing back this air, this force pushing down, it's also supporting this liquid. Yes?
If you push that far enough, would you be able to make the liquid appear as like if it was levitating? Or would there be like a...
Yes, I could do that, but then I lose the idea of how much liquid I'm supporting. Yes, I mean, if it was a high enough pressure, I could throw it out the other end. Please don't do that, okay? All right, so in any case, that's how a manometer works. Now, how is this manometer Torricelli's barometer? Well, Torricelli had a closed tube, okay? He had a closed tube. He had it all filled up. He connected to the air, and in a closed tube manometer, that's a barometer, okay? So, without further frost, let's get this down before I break it, okay? And let's get this down, okay? And let's go to some of these. These are pretty simple stuff now that we understand what we're measuring. And who developed these really idea of manometer? Of course, Torricelli. All right, so we'll do some of these together, and then we're going to take a little break. All right. So here we go with the middle part. We're just going to read these middle barometers together. I have to get rid of that. Probably want better pictures of that. And thank you for correcting my handle. I really appreciate that. Someone called me an old fart on the video and say, well, you know, the handle's not going right. I can just give you a worksheet of grams to moles all night. Oh my God, I'm going crazy. Okay, let's go different color because I can.
How about green?
I can't see it, so it's not going to work. That's like using white
Right there.
marker. Okay? How about we just use whatever color this is? Okay, so here we go, open
Yellow.
end.
Pink.
Who knows? Now, interesting enough, because he was the first to quantitatively express pressure in terms of how much mercury is supported, you should know that a millimeter of mercury being supported up a tube is the first unit of pressure. How much millimeters of mercury? And that is equal to a Torricelli. So you'll use the word torr from now on to express a unit of pressure. What does that mean? How much mercury is supported. So they're saying, if I'm not mistaken, what's that say, 760 torr? They're saying the atmospheric pressure is 760 torr. Torricelli's, or 760 millimeters of mercury. Okay, being supported. Okay, so I have an open end. Look at the first one. Okay, this is mercury, Hg. All right, party people. The height above this is 52 centimeters. We should be able to convert that to millimeters. So what's that? 520 millimeters of mercury, or torr, right? Millimeter, centimeter is 10 times that of a millimeter. Okay. Now, who's winning? The gas in this chamber or the open air that's pushing down? Who's winning?
The air.
The air. The air has higher pressure than the gas by how much?
520.
Great. So what's the pressure of the gas if you know the pressure is 760? Minus 520. So you get what? 240. So the pressure in here is 240 torr. How does that work? It's losing. This atmospheric pressure pushed back the gas and it supported that much. Okay. What do we have here? Now I know my drawings aren't here, but here's where there's a brown gas. This is a different color. So this is actually the line of the levels here. So who's winning now?
The gas
Yeah.
The gas inside the chamber is winning by how much? 67 millimeters of mercury, or torr. So therefore, the gas must be that much higher than that of the atmospheric pressure. So that would be what? 760 plus 67. And so you get 827 torr. It's that easy. Now, closed end. Anytime you hear closed end, you can assume, don't be a donkey or an asymptote, you can assume there is no pressure in that area. That's a vacuum. And there's a reason why mercury creates a vacuum when it falls down. It doesn't evaporate very well. At atmospheric pressure, I used to have a vat of mercury. I used to be able to do that demonstration really cool before I could tape them so easy. Now they don't want any mercury obviously exposed to people because it's a heavy metal, gets in your body, Manhattan disease.
And you can make bombs
Yeah.
with it.
But that too, okay? But the other side to it is that people think, well, it's going to evaporate in the air. At atmospheric pressure, there's 0.0001 evaporation, so it doesn't evaporate very well. Any case, as soon as a vacuum, okay, the levels are here. So this gas in a closed tube is just supporting the liquid. How much liquid? Which is equal to what in millimeters?
103.
Millimeters of mercury or torr.
So
And that's it. And hello, a closed-end manometer
no one.
is a barometer. That's what essentially Torricelli made to measure his problem. Okay? So these are very simple. The point of the manometer is to be able to see them in other problems. Okay? And that's what part of your homework is, to do the word problems, to see the manometer. Now if you go to the other page, flip this over 11 times. Okay? You can see there's some more pictures, and I'll just quickly talk about them, but I don't want to spend any more time because it is an easy skill. Okay? You can check your understanding of that. Okay? If you look at the bottom, okay, you gotta make sure this is a closed-end tube, closed-end tube, closed-end tube. So you gotta be careful when you see an open-end tube. Open-end. You gotta be careful. You gotta know.
Do they not tell us?
They usually do. In these pictures, I'm showing you that.
Okay.
So if it's closed-end, it's just what? Okay. Yeah. Now I think that's that's hard because they might be all open-end. I gotta tell you, I have to look at the key. Maybe these pictures are red. Okay, but it doesn't really matter.
It looks like it's
They
open,
look
closed,
different.
open,
They
closed.
look different, and if I look at, someone pulls up the key, I think there might be all open, and I think my pictures are bad. Okay.
The pictures are very bad.
Yeah. But look at let's look at this one right here. This one I can see definitely there is, so this gas has what? The same levels. So what's it tell me? That the pressure outside equals the pressure inside.
So it's just,
Yeah, and notice I'm using a different unit.
you gotta convert.
Yeah, and so we're gonna stay away from those from right now, okay? So if we just did the first page, it's good enough, okay? Hello, this is what? What do you think this is?
Oh, it's that.
Yeah, they're all that. They're all manometers, but this is a particular type. This is a barometer. Whether I can do it this way in a pan or write it this way. All right, so you could do the ones that are torr Atmosphere. 1 atmosphere equals 760 torr. Forget about the other ones. Maybe we won't. Okay. We're gonna take a break now. All right. I'm gonna stop that.
Gravity.
We're doing the ones that we can do,
The
I forget. I
Are we
think the picture.
considering a closed end?
manometer key isn't on here.
It's not.
No, our homework for Thursday says that we have 2 gas laws worksheets.
No, you guys have 3.